Hello and welcome to the last assignment of computational tools for big data. The subject chosen is TensorFlow, which is Google's open source platform for machine learning library. It applies deep learning to different areas and was released on the November 9th. The usage within Google right now is the speech recognition and image recognition areas. And the vision of publishing this tool is that to create one set of tools for machine learning to enhance the experience of communication and collaboration between researchers and practitioners who uses the models. The key point is that the TensorFlow creates a model in the form of flow graph mimicking the neural network structures, and it also runs on multiple CPU and GPUs to enhance the performance. Currently, the TensorFlow supports Unix, iOS, and certain mobile computational platforms. You can grab it by using pip install. There are a few package dependencies that you need to make sure it's up to date. And you can also get the newest file changes from Git clone. It's on Google Source. There's been a lot of new tutorials and data files just within the last few days. So it's very good to keep an eye on what's been changed on the Git clone. As mentioned before, TensorFlow represents a computational model within a graph, and there's two stages of using TensorFlow. The first one is to construct and assemble the graph to create the nodes and the interactions between the nodes. As we can see, the flow between one node to another is a tensor being sent as output from one node to another node as input. And at the end, you can execute the entire graph and get results by using TensorFlow sessions. The nodes on the graph in TensorFlow is called ops. It stands for operations, and it's essentially a computational function with input and output as tensors, whereas tensor is a multidimensional array consists of a certain rank, shape, and type. And here we can see a table of the different ranks there are. The ops, or the nodes, within the TensorFlow graph have different various types. The first one is a constant, and this is an ops that does not take any inputs. Rather than you assign it to a fixed value and it stays that value throughout the entire graph execution. And the second one is a variable, where you define it from the beginning with a value and a name, and that value can then change throughout the execution by using the assign function. The important thing about variables is that it must be initialized by using this command, or initialize all variables within every graph sessions. And the last one is a placeholder, where you define the data type that you expect to get within this variable. So this can take in any file as a tensor and to use it within a function. So this is the most flexible one of the three. TensorFlow is then used to create an example of a deep convolutional MNIST classifier, where it uses the dataset from MNIST, which is a large database of handwritten digits. So this is my attempt to recreate the MNIST multi-layer convolutional network classifier on the handwritten digit data. First of all, we gather the data with the built-in function from MNIST, and then we start the interactive session for the TensorFlow graph, and then we define the first iteration of ops. The first one is the image, which we expect to be 784 pixels large, and then the Y will be the target output, which consists of a 2D tensor, each row consisting of one hot 10-dimensional vector. And the 10-dimensional will be the 10 classes from the digits 0 to 9. And then we define the weight and the biases, which will be helpfully calculated by these functions, as well as the convolution and the pooling. Then the construction of the network consists of the first two layers is simple convolutional layers, where the first layer has 32 features and the second layer have 64 features. These are almost identical except of the number of layers, and they're being stacked on top of each other. and the result from these from the second convolutional layer will be sent to the densely connected layer, which is a fully connected layer with 1024 neurons, and that will send the output into the dropout layers to figure out how to automatically handle the scaling of neuron outputs. And this is used in this function. We use the built-in dropout function to create results that will be put into the readout layer of then uses a softmax regression method to tell us the image falls with which probability into which category. And at the end, we initialize the training and evaluation method. As you can see, we run a 20,000 iteration training with logging every 100 iterations. At the beginning, the accuracy is rather low, and then it starts to grow and stabilizes towards 1. And at the end, the test accuracy, which is printed here, is 0.9909. The next step is to try and recreate the recurrent neural network within TensorFlow, and the RNN has the advantage of allowing information to persist by introducing loops within certain layers of the network, and that gives the possibility of storing context, so for the network to produce more precise and more meaningful results. For example, in the video, if one frame is being sent to the CNN itself, then the previous content will be disregarded, while the RNN will be able to take some of the context and store that into what's called the long short-term memory, and then use that information to help the recognition of this particular frame. And the application of these RNNs are within machine translations, for example, for predicting next words or next letters within one word. In the attempt to recreate the recurrent neural networks example from TensorFlow's tutorials, I met the problem that at the very last step where you are supposed to run the code, it turns out that I have not correctly set up the Basel, which is required for this very particular tutorial. And because that was not correctly set up, the script itself did not produce any results, and it had difficulty finding the data path to the required data used for this RNN. The last two that I'm trying to test with TensorFlow is the tool called TensorBoard, which is a built-in interactive visualization of the computational model that we just created. In this model, as you can see, we can see the ops and the flow of tensor between the ops. Interactively, you can enlarge each ops and see the functions within, and as well as there is a histogram tab on the TensorBoard where you can see the results from the machine learning process. In the attempt to use the TensorBoard to visualize the graph that we created in CNN, the correct connection is established to the browser, so the TensorBoard interface is shown. The problem is that the connection between the session and the TensorBoard is not established correctly. As we can see, there is no information to be shown, but we can still click on the possible outcomes that can be created using TensorBoard. So the conclusion is that TensorFlow can have the potential to be very, very popular for any machine learning problems, as it can apply deep learning in a very intuitive way. And as for me, the immediate next steps is to set up Basel correctly, so that I can run the RNN and be able to predict the immediate next words and letters within a sentence, also applying word embedding, and also to establish the correct connection between a current graph session and the TensorBoard to be able to interactively view and evaluate the model.